Now, this year's Nobel Prize in Physics went to a team of scientists for their work that led to the observation of gravitational waves, described as a discovery that shook the world by a Nobel Committee member. The detection finally confirmed Albert Einstein's prediction about the existence of gravitational waves 100 years after he published the idea, and it's a great honour to talk to one of the recipients now, Barry Barish, Linda Professor of Physics Emeritus at California Institute of Technology. Thank you so much for speaking with us.
Oh, thank you. Hi, I'm here.
And I read that you described this as an undeserved prestige, a responsibility to be a spokesman for science. It seems that you've been very pleased to receive the award, but that you also recognise what comes with it.
Yeah, that's what I was referring to. Not certainly the science that we did, we'll talk about in a minute, is worthy. Whether I'm worthy of carrying out the extra that come along with the prize was what my remark was about.
And that includes having to take a position on areas of science that would not necessarily fall within your expertise. Global warming, for example.
Yeah, I think there's many areas where the opinion of scientists are not carried as strongly, at least in my country, as they should be and need to be in order for us to move forward as a country in the way we want, whether it's informing the public or our government. And a good example, I think, is global warming, where it's become so much a political issue. Whether politicians believe it exists or doesn't exist depends on which party they're in, rather than listen to the views of scientists.
Speaking before about deserving awards, it is interesting that when we look back to October 2016 in Science magazine, Adrian Cho wrote that next week the 2016 Nobel Prize in Physics will be announced, and many scientists expect it to honour the detection of ripples in space called gravitational waves reported in February. He was expressing concern that you, Barry Barish, might miss out, and he was concerned about that because he said that as this award may be split three ways at most, you might not be included on the list. As it turns out, the award was handed out in 2017, and one of the potential recipients sadly passed away in the interim period. Can you just address for us the complexities of the way this Nobel Prize is handed out, and how you've felt about that in the interim since this discovery was first unveiled?
Sure. First, it's a complete mystery what criteria are used, only because the Nobel Committee doesn't share their process with the outside world. So other prizes, that's more shared, so people know what's involved here. I can't speak for it at all. All we know as people, whether we're scientists or anyone else, is what criteria they've appeared to use in the past. I think here the question was, this is a long effort. First, it was 100 years ago that Einstein predicted gravitational waves. He had some doubts 20 or 30 years later. It became an experimental subject in the 1960s, 50 years ago. And this technique that we've developed was starting to be worked at about 40 years ago at the beginning. So in a 40-year process, who matters? I think it's a very complex problem. In this case, the people, the group of scientists that kind of got the idea rolling in different ways, from a point of view of the science that you could address, from the point of view of the technique that would be used and what the complexities were, and from the point of view of kind of what clever innovations might be incorporated, was conceived of by three people that don't include myself, who are often referred to as the founders. In other words, they more or less started viably the experimental effort. And the experimental effort went on for another 20 years. By the time I joined, it was 1994, 20-some years afterwards. There still was no project, but there was an idea that had been developed. Small prototypes had been built, and then we start a project, and then people build the project, and finally people analyze and study the data, and somewhere along the way, how do you decide who matters and who doesn't matter? And that's the question that was posed. In this case, there were three very identifiable people at the beginning, but after that time, the role that I played in many people's mind was so crucial that how could I be left out? And that was where the process was.
And it's wonderful to now speak with you, having been honoured for that work. You were the director of the LIGO Gravitational Wave Observatory from 1997 to 2005, involved in the design of this instrument, the construction of the facilities themselves too. And what we're talking about here, this is where I get a little bit lost, and perhaps you can help us, is the detection of waves created by huge events or massive objects, by pairs of black holes coming together, merging. Can you explain that in ways that we might understand?
Yeah, and when I explain it, it'll sound pretty unbelievable. First, we should go back and say, what's a black hole? Because we're talking about black holes. And there's different kinds of black holes, but it means the same mathematically. What we refer to as a black hole is a region of space where matter has come together in such a dense cluster that nothing can get out. The gravity is just too strong for anything to get out. And mathematically, we can calculate what that takes. The kind of black holes that we are talking about as I go on in this, and for gravitational waves, or at least our observation of gravitational waves, are what we call stellar black holes. Stellar is the word for stars. And so it's when a star burns up all its fuel, including our sun, it works by a nuclear fusion process, and eventually it burns up the light elements and the heavier elements, and eventually it burns up all the elements that can create nuclear fusion. And at that point, the pull on it, just because of the masses of the elements that are there by gravity, makes it collapse into a small center. It collapses as much as gravity can pull it in. It's mathematically true that our own sun could not make a black hole. If you take our own sun, it's too small to make a black hole. But if you take other stars that are more than, 2 or 3 times the mass of our sun, then when they collapse, depending on the details, they can make a black hole. And so that's what a black hole is. The black holes that we observed were about 30 times the mass of our sun. So you take our sun, that 30 times the mass of our sun. Those were totally unexpected. It was believed that there were no stellar black holes that are that size. But the way we observe them is they happen to be there at that size. Not only that, they happen to be there in order for us to observe this, enough of them so that one can be captured around another, and they, by gravity, pull on each other and orbit each other, very much like the Earth orbits the sun. It's pulled by the sun, and it orbits around the sun. So you can have two objects going around each other. But if the accelerations are very large, it turns out by Einstein's theory, they radiate away gravitational waves, which is what we'll end up detecting, and they merge into each other. The actual phenomenon, when we saw it, was the very final merger, the very final. This merger may go along for millions of years, but eventually it gives up enough energy so they come in and crash. We detected the last 0.2 of a second in this crash. And during that time, these two objects are going around each other at about half the speed of light before they merge. They're each only about, I would say less than by far than the size of Seoul as a city. They're smaller than that, but their mass is 10 million times the mass of the Earth. So you have to consider these two objects each have 10 million times the mass of the Earth concentrated in an area smaller than Seoul. And they're separated from each other by less than the size of Korea, South Korea. And they're going around each other at half the speed of light, and then they crash together, and that's what we detect. We detect the way the energy comes off by Einstein's equation is what we call gravitational waves. And the way to picture those is think of a very still pond of water, and you throw a stone in the pond of water. The stone sinks to the bottom, but there's waves that travel out circularly from where the stone entered the water. There are little ripples that pass out. This is very much like that. They're ripples in space, not ripples in water. They carry energy, as those little ripples actually carry a little bit of energy. And we detect them once they get to the Earth. This actual object, a phenomenon that we observed, happened 1.3 billion years ago. And the signal finally got to the Earth. It was far enough away that it took that long. It got to the Earth just at the time we were able to build a very sophisticated detector that could actually see or detect this event.
Just incredible.
That was a lot to swallow, but it's a lot for me to swallow as well.
Well, thank you so much for sharing it with us. And it's a privilege to speak to a man who you take away a few years and a little bit of space, pretty much working alongside Albert Einstein on this. And now your name is right there all over the headlines, or has been anyway in the last few weeks. Barry Barish, Lynn Professor of Physics Emeritus at California Institute of Technology, but a Nobel Prize recipient for physics this year. Thank you so much for taking the time and speaking with us today.
Thank you. Thank you. Thank you. Thank you. Thank you. Thank you. Thank you.